Good morning. Welcome to Krishna's classroom. So let us consider the concept of unitary operators on inner product spaces. Before that, we just recall whatever we did for positive definite operators and semi-positive definite operators, whatever they are. Okay, so let us start with the following. Let X be an inner product space of dimension that is, we are considering finite dimensional inner product spaces over C or R. I mean, it could be both, over C generally, sometimes over R. Now, what we have observed is the following. If your inner product space is X equal to C over C, then dimension of X equal to 1. And the inner product there is given by the inner product of alpha with beta is defined as alpha beta conjugate, where alpha, C. So alpha and beta belongs to C. So that's the inner product that you have. Okay? So it is a one-dimensional space on which you have an inner product space. Now we know that every linear transformation on C can be identified with a scalar. That is, if T belongs to C, then Tx where alpha represents T in some, that means we choose a basis, and with respect to that basis alpha represents T. Therefore, T, the matrix representation of T is given by alpha, or this is a 1 by 1 matrix where alpha is a complex number. Okay, so alpha is a complex number. So every complex number, once you fix the basis, it represents a linear transformation, and the operation is defined by multiplication. Conversely, if you have a linear transformation and once you fix the basis, then it is once you fix the basis, then it is represents a linear transformation. So this identification is there. So C is identified by This is what you have. Okay, so we keep that as a result over here. Now what next? Yeah. So this is the inner product that you have in the one-dimensional case. Now, in the one-dimensional case, LC is commutative. Is commutative multiplication. In fact, if you use any inner product space, one-dimensional and inner product space over C, then this will give you the class of operators form a multiplicative set, that is it's commutative with respect to multiplication. That means you will get T S, where T belongs to dimension of okay. So that's the position that you have. It's a commutative collection. Okay, but suppose dimension of X is greater than 1, that means it is greater than or equal to 2, then T and S may not What we have seen is this: the analogy of the behavior of complex numbers gives lot of insight into the properties of operators. That's the most interesting part. And what we have seen is this: if alpha is real, then we have alpha representing a self-adjoint operator. This is because alpha belongs to C if it represents a linear operator, T say, then T star is represented by alpha conjugate. And T equal to T star, that is T is self-adjoint if and only if alpha equal to alpha conjugate. That means alpha is real. Now this is the scenario that you have. Okay. So in the complex plane, you see that the real line, all points on the real line correspond to what are called self-adjoint operators, others do not. Okay. So alpha this is the result that you get. Okay, right. Just using alpha for T. This is what you have. So this result is something that we have. I mean, I am using both T and S. So T is represented by alpha. This is what you have. So T is self-adjoint if and only if alpha is real. Okay, so that is our contention. So if you have a T represented by some alpha here, T, then you see that alpha conjugate, this T star. This is the complex conjugate I am talking about. So if T is represented by alpha with respect to some basis, then T star is alpha conjugate. This is the result that you have. So it takes T star is essentially the analog of complex conjugation that you see. Now you look at the special class of operators. If alpha belongs to C is such that alpha conjugate equal to 1. Okay. So 1 corresponds to I. Okay. Then and the analogy that you would have, if T is alpha, then T star equal to alpha conjugate, which is equal to 1, say, then T is what you call unitary. That means it lies on the unit circle. So every point here on this represents what you call an operator with the property that T star is equal to I. Okay, so that is the analogy that you have. Okay. And unit circle corresponds to operators. T such that T star that is what you have. Okay. But when you go to higher dimensions, there is no commutativity in general. You cannot say that T commutes with S. However, see, there are the commuting class of operators and general operators which do not commute. Therefore, what you have is the whole. For a while and stop. So we now take up the general case X C. We look at what are called LX. So, okay, we take dimension of X. Now we see that T is, see, T is self-adjoint. Corresponds to the complex numbers which are real. So the property that you have is this: alpha belonging to C, alpha real, conjugate, correspondingly T belonging to Lx T equal to T star. Now T star corresponds to complex numbers of the and what we have is that T equal to T star is a statement which is a generalization of alpha bar, that is alpha is here. That is the analogy that you have. Okay, so let us ask this question. So what we have considered is the following. When is real and positive? This is the question that we have asked. You have seen two alternatives. Positive. There exists a beta belonging to C such that beta square equal to alpha. The second property is that is also if and only there exists sigma belonging to C such that equal to alpha. So both these statements are true. What are the analogous statements that you have? Say that T is positive let us call that positive if T is equal to S square yes, some self-adjoint operator, yes, that is one thing. The second property is that the second property is that, now this is again if and only if there exists a S belonging to C such that for some S belonging to, okay. The third, the inner product of these are the three properties. So let us prove these results. The first thing is the following. So we can show that, suppose 1, the first statement, suppose 1 is that there exists S self-adjoint such that two third statement is so what we have proved is this. I mean, these are trivial. 1, 2, and that implies 3. So it remains to show P is self-adjoint and then so that you would have 1 implies 2, 2 implies 3, 3 implies 1, okay, but we postpone the proof. I think you have to wait for some more tools to prove this. In fact, once you prove the spectral theorem for self-adjoint operators, now this is just one line from there. Okay. So we will just use this and define T is positive definite denoted by equal to 0. T is self-adjoint and inner product of okay. So this is the definition of what is called positive definite. So using this idea you can, and we say that if T and S are then t is greater than or equal to s, if t minus s is positive definite. Okay, so we write that is or you have the so in that case we write it as t greater than or equal to s. Now we make the strictly positive definite operators. T is said to be strictly positive definite if and greater than 0 not equal to 0. Okay, or txx equal to 0 only when this is the definition of what you call strictly positive definite operator. So some of the terminologies that we use are now, in fact, we shall prove a little result. Says that if t is strictly positive definite, then t is invertible. Now the proof of this result is this. This follows from the following. That is, we have tx for every x. This is from the Schwarz's inequality. Okay. Now what do we see what we want is t is invertible if and only if see t is invertible if and only if Tx equal to 0, 0. That's what we want to prove. So it is enough to prove this. So what we want to prove is the following. T is strictly positive definite implies T is invertible. That means we have to prove Tx equal to 0 implies see, we have, if x is not equal to 0, then we have what we have? We have 0 is less than mod Tx This is what you get. Therefore, x is not equal to 0 implies norm of x is not equal to 0. Then, if Tx equal to 0, then we have for some, see, this is equal to 0. Okay. Which is not possible, because you have this inequality 0 less than this. For some hence Tx equal to 0 implies x equal to 0. That is so every strictly positive definite Let's want to solve that way immediately. Further, T is invertible, T is strictly positive, T is self-adjoint, and T is invertible. Then T is I think I will write here positive. T is strictly positive definition. So what we want to prove is this. Equal to 0 implies x equal to 0. Okay. This is quite straightforward once you assume the invertibility. So let us now consider what are called the unitary operators. So I told you in the beginning that unitary operators are analogous to the complex numbers on the unit circle. This is the analogy that we have. So let us see what all things come out of it. So what you have is u star equal to 1 corresponds to I. So what we expect is u has the property that norm of u equal to, okay, let us work that out. But we first investigate the properties of complex numbers on the unit circle. So let us get back to the complex plane. Consider as a linear transformation on C. then what you have is that Tx, Tz, Z belongs to C. What does this do? In fact, so this is what we have to look at. Look at the complex plane, take any Z belonging to that, and this can be written as R e to the power I theta. This is the angle theta that you have, and R equal to, that's it. Now take any alpha. Theta 1. This angle is theta 1, and then what you call R1 equal to, so alpha equal to R1 e to the power I theta 1. Then R1 is equal to mod alpha. So you see that mod, see, alpha Z belongs to C. And what is this? Alpha Z as the representation is R1 e to the power I theta plus theta. So what does this particular vector do? So alpha, multiplication by alpha corresponds to turning the vector through an angle theta 1, which is equal to argument of Z, and multiplying it mod alpha. That's what you have here. So you are multiplying by R1 and then changing the argument from theta to, that is, theta is changed over to theta plus theta 1. R is changed over to R1. This is the transformation that is taking place. So two things are happening. One is rotation through an angle theta 1, and scaling the vector by the factor which is equal to the modulus of alpha. So two things are happening. Thus multiplication by turning the vector argument of alpha and scaling factor mod alpha. This is the action. Okay. So this is what we see in the complex plane. So what happens? I mean, we make certain observations. Suppose you take two vectors z1 and z2, okay, and then multiply both by the same complex number alpha. Originally, the angle between z1 and z2 is given by argument of, okay, right. See, then we observe the following. Okay. First observation is that the angle between the same as angle between alpha z1 therefore the angle between the two vectors is an invariant under the transformation T. Okay, so that's the one thing. Suppose mod alpha is equal to 1, then Z and alpha Z have the same that means the length is preserved by this, provided this condition is true. Okay. There of course it is irrespective of this as long as alpha is not equal to 0. So we shall see the similar properties true for what are called unitary operators. Okay. We also observe that if alpha conjugate equal to 1 then alpha inverse, this is also an observation that we make. What are the analogous things? So we now define what is called unitary operators. u star So you have u star x. Okay. Then what do you have, which implies or u is equal to this. U is invertible and this is true. Now we just prove a little theorem, which not too many things are there. Let us make the statement of the theorem. Okay. So this is the definition that you have. So we prove the theorem. X is finite dimensional inner product space over C. The third property is that okay, let us prove this. Assume one. You have equal to y this is true for every y. So that is that's the first part. Now assume 2. Now 2 implies 3. This is put x equal to okay. Now 3, assume three. Then U star U equal to why is it so? Because what you have is this. Because this is what you have, that is assume 3. You have U star here we have used that U star star is equal to U, and there of course we are working on a finite dimensional inner product space, therefore U star star is equal to, that is true for any operator. So, therefore that implies now this is true, so that implies because this step comes from the following. Okay, you see that you are saying X is orthogonal to this whole thing, or this is orthogonal to every X. That is possible only if this is equal to 0. Therefore, you have this first result. Therefore, we have these 3 statements are these 3 are equivalent. Now a consequence is that, corollary is that that comes from here. Simple. This is U minus U of X minus Y equal to norm of X minus Y. Okay, what does all this mean? See, this is a measure of the angle between Ux and Uy, and that is the same as the measure of the angle between X and Y. This is one result that we have observed earlier in the case of complex numbers. Here again, you see that this is the distance between ux and uy is the same as the distance between x and y. So, if u is unitary, then you see that it has a property that it is angle preserving as well as lengths, distances, and angles. See, this is length preserving, this is distance preserving. Now, this is angle preserving. So, these three properties are there. Okay? So, that is the important thing about the unitary operators. Therefore, ux equal to 0 implies this is because norm of, therefore u is invertible, and that's the result that we. Now, what are the other properties of this invertible operators? Let us examine that. It preserves the orthogonal, okay, it transforms an orthonormal basis into an orthonormal basis. So the next theorem is it transforms every orthonormal basis into an orthonormal basis. Now, this is a consequence of the following. Let orthonormal basis of x delta h. Now, consider this. is orthonormal. Okay. So I think we'll conclude this talk with this remark, and thank you very much. Continue with it in the next lecture.